Well, thank you all for coming to the afternoon tutorial. I am very pleased to welcome an old friend of mine, whom I've known for almost 20 years. Being you, she is the Chancellor's professor at the Department of Statistics and also at the Department of Electrical Engineering and Computer Science in University of California, Berkeley. She got her PhD from Berkeley and then had various positions at University of Wisconsin and elsewhere, and she's been in Berkeley since the mid-90s or something like that. So her work has spanned quite a few areas within statistics and related fields, and in fact she has done, starting with her PhD thesis, she did work on information theory, particularly in rate distortion theory, and also on the minimum description length principle. Lately, her work has been concentrated on large data problems. She is a fellow of the IEEE, a fellow of the Institute of Mathematical Statistics, and this year she's the Tukey Lecturer of the Bernoulli Society. And she's currently the chair of the Department of Statistics, succeeding people of the caliber of David Blackwell, Lucien Lecam, and Jerzy Neyman. So, Bin.
Thank you very much for the kind introduction. So I'd like to thank the organizers for having me here today, and it's a tall order to follow to speak after David Donahoe and on very related topics. So I'll try to emphasize the orthogonal bit of my talk, in my talk. So first I'd like to advertise for the Blackwell Memorial session tomorrow, I think after lunch. And especially I want to really like the quote from David I learned when I was a graduate student in Berkeley. He said, I think I read in a newspaper when he was interviewed, basically I'm not interested in doing research. I don't think many of us could say that. And I never have been. And try to do that for a grant application. I think that would get us into trouble. But he clearly says that I'm interested in understanding, which is a quite different thing. I think it's always good to remember that. And the session is tomorrow, and David passed away at the age of 91 last year. So as Sergio said, I've been working a lot with different kinds of data and try to do the theory, which will give me insight into data. Earlier of my career, I did a lot of theoretical work for the sake of theoretical work, and right now my take on theory is very much from the angle applied work. Try to use theory to give me some insight so it help me to solve the real problem. And I've been working in the general field now called statistical machine learning or machine learning, and machine learning has made much progress in terms of prediction. And I think the field is slowly turning or quickly turning into interpretation and sparsity, which what we call, David called compressed sensing, which is a different take on the same sparsity from the design angle of sampling. And the sparse modeling field in statistics is more passively observing how the brain might have reacted without the luxury of designing it, and to try to understand things which when sparsity might come into play. I'll show you two examples where we take advantage of sparsity in one science example and one social science example, and show you how we validate actually beyond mathematical statistics using other information. And I think, as I said, what I hear is that you have this new field called computational social science, and maybe take advantage of that. So I think in terms of notation, my P is David's big N. I think my little n is the sample size. So a little notation change. And computation was very much in David's talk, which I will briefly cover a little bit of that. And I will be concentrating on this L2 estimation error for statistical information extraction. And machine learning has widely applied to web search, document analysis, which I will talk about example, and bioinformatics and sciences in general. And there are many successful machine learning methods, support vector machines, semi-supervised learning, spectral clustering, and I see sparse modeling as one of those tools in the toolbox. And in statistics, we usually, when we talk about sparse modeling, we include boosting, which is like related to ITA boost, but with a shrinkage step, and you see a lot of connection between that gradient descent of a method with early stopping and the penalized version of sparsity like Lasso. Since this is a tutorial, I'll be more than happy to entertain questions during my talk, so just raise your hand and I don't have to finish what I prepared. So here's the roadmap for my talk. I like to use a neuroscience example. Some of you might have seen early version of that because I've been working with the Gallant Lab in Berkeley for the last 5 years. And then I want to take a different angle than David. David I felt like took the applied math angle, the history and precursors to Lasso. And now I'll take like statistical angle on this sparse modeling and start with Occam's razor, more in terms of modeling and also from model selection from the 70s. And in terms of the tutorial part, I just want to share some, I think, insight we recently obtained with co-authors on why high-dimensional estimation is possible. And it turns out to be quite simple after you understand. I think actually we took a very abstract form and did some clean mathematics and really realized that a lot of the examples we have done before, including us and co-authors, can be really nicely unified under this general mathematical framework. And I'll be talking about rates. I'm now doing the constants as David talked about. And then I'll come back to the neuroscience basically project and tell you what we end up doing there. And then I'll move on to social science, where we actually try to use sparse modeling to do document summarization. And there we just took off-the-shelf method from sparse modeling. But the work was a lot of pre-processing, different way of normalization, different way of evaluating, and we ran a human experiment with real subjects. And for them to really give validation to our summary of basic corpus of documents. So I think the other one, the other big blob is a test on the hardware at UCSD. So you couldn't see anything. I'll talk to Alon to make sure that you have the precision next time. Because for some better projectors, I could see the shade of different colors, but now you don't. So here is something actually easier to see. It's from, I lifted from internet. It's Da Vinci's drawing how brain works, right, 500 years ago. So the eye is like a camera, and you have different optical time devices, and then the signal gets projected to the back of the brain where the visual cortex starts. That's what I'll be looking at. Okay, so the early visual area. And here, supposedly, if we had a better projector, we're going to see the brain, the cortex is kind of use Galant's words, would be like a scrambled basketball. So when you make that flat, you can see that V1, the early region, will be mapped on the flat surface here. And they're supposed to be on my screen. It's gray and then orange and red and black and gray. Okay, so try to imagine those colors. And the data I'll be looking at, so the Gallant Lab is like a frontier lab in neuroscience. And traditionally in neuroscience, people used to use white noise, grating, sparse, and things like that to stimulate our brain. And Gallant Lab probably is the first lab who used natural images. And you can see that there are pros and cons to both approaches. And they do have physiology data, which is single neuron data, but the data we have been looking at is fMRI data. So this is not a child, so this person can lie there for hours at a time. Actually, it's a postdoc, so he can even lie there longer because his own research rely on his data from his own brain. So he's used his own brain to analyze the data from his own brain. So it's kind of, and so usually 2 or 3 hours at a time. I definitely wouldn't want to lie there. I'll go crazy. And then there will be, so for those of you who don't fMRI is a very aggregated, indirect neuron signal, right? So first, is the voxel, a pixel or voxel on the fMRI scan is about hundreds and thousands of neurons aggregated. And also, the time resolution is not that great. It's like seconds. And, but still, it's not an invasive technology, so you can do human experiments. And it really measures the baud signal, basically oxygen change in the blood flow. So it's not like a single neuron, you're measuring spark trains. So keep that in mind. And the Galant Lab made a Nature News with a very, very catchy title, Mind Reading with a Brain Scan. Right, so actually DARPA, they have been dancing with DARPA. DARPA might have some interest in them. I don't know whether Jack actually got money, but definitely DARPA was interested in talking to them. So they basically used a forward model. I'll tell you what it means, encoding model, and then use that model, did some decoding. So basically, based on somebody's fMRI signal, they could guess, use the signal, estimate what image the person could be looking at. So they played a little trick. So it's not. So they know the image is 1 of the 120. So it's a little like classification with 120 categories. So it's kind of limited, but still was, I think, surprising that they could do that. And what we will go in our decoding game, we actually will add tens and thousands of images we know the person was not looking at and try to ask the person to, the algorithm to decode the right image. So we're adding kind of noise images. Eventually, of course, you think that you can put all possible images in the database, and then you can pick the right one. Even it's cheating a little bit. We don't really understand how brain works, but in terms of recovering what the person is looking at as an engineering problem, we succeed. So that's kind of where I think DARPA is interested. It doesn't really solve the basic neuroscience problem, how brain works, but we end up, can guess what somebody might be looking at without understanding exactly how it was done. So the natural images Galant Lab uses here's the example. So the images are now controlled for quality, different resolutions taken by different people, some from Flick, some from the lab members themselves. And the image database, they have much larger one we've been using, is about 10,000 images. And there is a design, which actually, this will be another talk. We discovered that even though they try to randomize the images, so the Galant Lab want to kind of come up with this IID design. So they randomly choose an image from the database and show it with 1 second apart to the subject, and then they stop for 3 seconds for the mind kind of to forget what they have seen, and then they will do another round. And it turns out, when after you have the time series data, they only did a randomized block design, and that has impact on how you estimate the signal-to-noise ratio. So one student, Benjamin, is working on that, really, I think, making great progress. So it's really, the first batch of data we got actually was from already with the time signature removed, it's scrambled up. And after we asked the raw data, you can actually see a very strong block structure. But we're not considering that right now. And then you have the fMRI machine. I think it's a faulty machine, pretty strong. And then the lab did a lot of pre-processing to remove systematic kind of offset, like your heartbeat will have a trace there. So they did some PCA, and that part we didn't touch. That's also could be problematic. But so we get the response signal actually nicely Gaussian. Okay? And the signal itself observed is not negative, right? It's all positive intensities. But after pre-processing becomes Gaussian centered at 0. Okay? And based on past knowledge, this is where people think that V1, we are like doing Gabor transform, right? There's physiology data from a Nobel Prize winning work by Hubble and Wiesel in the 50s. And there was very nice work by, in Science 1997 by Olhausen and Field, from 2 ends, kind of showing that, yes, it seemed like V1 works like Gabor filters. So the physiology data was doing experiment, and the other data is from natural image side, doing something like ICA or sparse coding. So basically, if you believe nature and brain co-evolved, then you should discover this truth about Gabor filter from both sides. It's embedded in the natural images and also from the physiology. So that's well accepted. So V1 works like Gabor filter, and with different orientation, different frequency, and different location. Okay, so it's well known that V1 will only respond to certain directional bars and at certain location. So this is try to cook up in an analytical way, like a rough approximation to all possibilities. So now when my image is 128 by 128, and gone through these Gabor filters, it's known that V1 doesn't care about phase, so we did the norm, remove the phase information, so it's just shifted. The first two filters are really 90 degrees shifted of each other, so we take a norm of that, and we remove the phase, and then we expanded one image into a vector of 10,921. So that's my P. Okay, so now my image is represented in a vector, which is overcomplete, and I cannot reconstruct the image from so it's not a one-on-one because the phase information is lost, and we know that phase information is very important. So now to phrase it in a statistical framework of statistical notation, we now have a problem trying to predict the fMRI signals, which is called, in computation neuroscience, is called the encoding problem. From input, can you predict the brain signal? That's called encoding or forward. And the other way, from the brain signal to estimate the input, is called decoding. So now I'm developing an encoding model. So you have, again, this underdeterminedness, right? I have P almost 10 times, 5 times as big as my sample size. And of course, Galant Lab want to understand human visual system, and they want some model they can take a look and they can understand. It doesn't mean that the model we find through predictive framework will be the one to really how brain works, but hopefully give some suggestive indications how brain might work, and we can do some other experiment to really confirm or refute. So Galant Lab, I think, is also one of the labs who try to say that we should really have some really, really serious prediction done to compare different models. So traditionally in psychophysics, people use gratings and white noise and bars, and then they will build a model which qualitatively will give the features the experiment will observe. And they don't really ask themselves to fit quantitatively to the data. So this is a step forward in terms of model fitting to say that actually we want the model actually give good prediction. Of course, as we know, it's a ill-posed problem. And if you do, you have many solutions to these squares, and you will do bad prediction. You're basically going to be fitting noise because you have so many unknowns relative to the sample size. And Galant Lab, after many years, 2 or 3 years, they settled on, they rediscovered L2 boosting themselves. Even though I was telling them about it, but they said, well, we tried everything, it won't work. But the postdoc basically did refitting of residuals, and that's basically boosting, one form of boosting. And they were very serious about setting aside 120 validation samples. So they have 120 images. The response rate they don't touch at all, even for tuning the lambda parameter. Cross-validation, nothing, they won't touch. And this 120 validation sample is very nice because it's the same 120 images, and we have 13 replicates. So really high-quality data, much better than the data we use to train. And because I think tradition from physiology work, they use predicted square correlation. It's because it's known that even for spike-trained data, you cannot really predict magnitude of neural signal because that's related to intensity, and then it's not predictable. Therefore, you try to do correlation, so it's scale invariant. And that's why we inherit. We don't do mean square error, we do correlation for prediction. And it's interesting to take a look at how Galant Lab has been using machine learning or statistical modeling tools to do their problem, right? It's a lab I was very impressed. I actually spent a whole year there in 2006 just hang out and then get into neuroscience. And now one thing I was very, very impressed was that they were actually buying chips and building their own computer because they want to save money. And I was very impressed because I think if I tell my student to buy chips and build a computer, I'm sure nobody would do it. But they were neuroscientists and they were building computers. So they were very handy. They tried to solve their problem. And they started with neural nets as kind of parallel the development of machine learning, and they tried SVM, and then they settled with L2 boosting. So all these different three major kind of method groups more or less give similar prediction performance. However, boosting being or Lasso being a sparse technique gives them much, much simpler models. So they basically, before neural nets, right, it's many layers and it's not very well determined. Depends on where you start, you might end up with different structure. And boosting, as soon as you set a certain parameter, it's pretty consistent. You pick similar predictors and usually 20 to 70 terms. So it's much more manageable. And so this is really a shift, I think, in machine learning, that more and more people try to use simpler models. This is an information theory workshop I worked early on for MDL. It's really you want concise models for data transmission and faster computation and also for visualization. You cannot really visualize, say, example, the winning teams of the Netflix competition, right? Imagine to visualize that model, which is many, many models on top of each other. It's just very hard to see. So this is something I think more and more people like to look at. Of course, this going for simplicity is nothing new, right? This is, again, a Wikipedia courtesy, that there's something called Occam's razor. It goes back to 14th century. It says that, I think it's translated, maybe not. Entities must not be multiplied beyond necessity. I don't know if it's exactly his words, but says that if everything else being equal, you want to go for the simple one. That's kind of science has been following this simplicity rule. We have very nice, simple, I'll say, things to teach in classrooms, right? Otherwise, it would be hard to teach the Netflix model, I think, in any classroom. And so Occam's razor was already very much in statistical inference literature in the 70s. So Fisher, in the 20s, advocated the maximum likelihood, which is his version of turning Bayesian based posterior with an uniform prior into something likelihood-based. And but if you follow maximum likelihood with least squares, you end up with the biggest model, because least square is a projection. If you have bigger and bigger subspace, you're going to project for the bigger space, you have smaller mean square error. So eventually, you won't have any prediction power. Okay, so people realize that in statistics, if you follow maximum likelihood and compare between different models of different complexity, it just doesn't work. Okay, and moreover, if you have p predictors, for me I have 10,900 predictors, 2 to the power of p will be the number of possible submodels. And I'll go to this one first. So with that number, how many submodels? Is 10 to the power of 3,000. And David earlier made an argument saying that it's a combinatorial problem, NP hard, and therefore it's impossible. I agree, but I want to make another point, which I think is important to keep in mind, that for statistical problems with noise, you don't want to go through, even you have the computing power, you wouldn't want to go through these 10,003, 10 to the power of 3,000 submodels. With 1,700 data points, I don't think you can tell them apart. You don't have the precision to really say which model is better for 10,000, 10 to the power of 300 of them, 3,000 of them. You just cannot tell them apart. So it's useless, and it's wasteful of resource to actually do that. So that's another reason to say that with noise data, you can take somehow a path in all these possible submodels, and for a lot of purposes, especially prediction, that'll be good enough. Because the noise here is in your favor, in the sense that it tells you that you shouldn't go for very precise answers. You do optimization. I had this discussion with a friend of mine who's in optimization, I said, in optimization theory, you guys go to too high precision, 10 to the minus 5. And he said, well, that's how we define it. We have an objective function, and we care about the absolute maximum. But if you think how optimization is used in statistics or in anything related to data, the objective function we come up with is not holy at all, right? You change a few data points, you don't want the answer to change. And the statistical framework is saying that, well, actually, I'm going to use an empirical loss function, which is based on a sample. And the answer I get shouldn't differ too much if I have enough information if I get another sample. So we're kind of in pretense here. When we do optimization with data, we don't really care about the particular loss function we use. That's just a ballpark. That's just it's a random perturbation of the true loss function, which is expectation or infinite sample version, which we don't have access to. So therefore, when you optimize such a random function, which you don't particularly care, you should really bring in statistical precision to the game, not a numerical precision. So I've been working with a student on that, but it's kind of not easy to formulate. But that's just a point saying that even you have the computing power, you wouldn't want to go there. And also there are examples in data-driven world that to be conservative on computation sometimes falls upon you, actually bring nice regularization needed for better statistical estimation. There was a talk a couple of years ago by Google chief scientist, I think it's Peter Nowak, or the machine learning group leader. They just won, I think it was 2007, he came to give a talk to Berkeley. 2006, Google won the language translation contest with some Army, I think DAPA, like standard contest. And he was talking about that, well, how they did it. One thing he said was important was that they actually discovered that they were using some language model with some empirical probabilities. And first, they were coding the probability to the precision of 8 bits. And then they were running out of space. And then they start trying out with 5 bits, 6 bits, 4 bits, 7. And it turns out 5 or 6 bits actually worked better in terms of translation performance than 8 bits. So that empirical fact is not unrelated to what I was trying to say, because if you think about it, you have so many words, and the empirical probabilities are pretty noisy if there is a true one. And if you quantize, you basically make it more regular, more stable. And in the end, you do better statistical estimation. So that's kind of the same thing. I don't have a grand theorem to prove that, but I think most people who do data computation will agree with me. And therefore, I'm making the argument you don't have to go to this combinatorial search, and people didn't. Even in 70s, people quickly ran out of computing power, and they did a forward selection and backward selection. And forward selection is very much related to L2 boosting. So I'm just saying that this recent sparse modeling is really a reincarnation of model selection in the 70s in the statistical literature. And I shall show you the slide. I think I skipped. So in the 70s, a Japanese, I think it was engineer, but very statistical engineer, Akiiki, has something he called AIC, which is most people call it Akiiki's information criteria, but he says it's a information theory criteria. It's a panelized disgrace with dimensionality. So this would be, in modern terms, L0 penalty, because you're counting. And that's a combinatorial problem. And Schwartz, I think it should be 78, sorry, I got the date wrong. He did another penalty, but with different lambda, or different, he came from the Bayesian point of view, did the asymptotic approximations to posterior probability. And then that's where I worked a lot for my thesis 20 years ago, is resonance information theory-based or coding theorem-based minimum description length principle. So basically, a resonance formalized Occam's razor and really quantified in one way what we mean by simplicity. And that's based on universal code length. So you try to build a code length from a model with unknown parameters, and then you ask yourself to choose models based on this code length. And there's a close connection between resonance information approach and to BIC. Okay, so this is all L0. And jump to the 90s, 20 years later. And there, one paper, Chen and Donahoe, basically did L1 panelized least squares, now called Lasso. In signal processing, it's called basis pursuit, relative to matching pursuit, which is kind of L2 based. And before the famous Lasso paper by Tibershon in 1996, there was a precursor to that paper was by Bryman, who really did a lot for bringing the machine learning community together with the statistical community. And what Bryman did, since it's less well known, I would like to say a little bit, is an idea like start with least squares, so P has to be less than N. But then you put garage, like constraint, you put a factor in terms of all the coefficients of the least squares and ask the total L1 norm of the coefficient to be bounded. So you kind of constrain it. You pull the least square back by shrinkage using that. And if you read Tibershon's paper, he clearly cites Bryman for inspiring Lasso. And Lasso has been, if you haven't heard, probably you another planet or something. It's really getting a lot of attention because of the sparsity, the L1 constraint, the diamond. And you have a L2 loss in 2 dimensions. You have a contour plot. One contour layer will be the ellipsoid. And because the diamond shape of the L1 penalty, often the minimizing point happen at the vertices, often, or a lot of times, but it's no guarantee. Nobody has to actually prove that one will happen, but everything's, and in practice, it does happen that most of the time you end up on the vertices. And the vertices is model selection, in the sense that because you're selecting variables, you're setting the beta 2 being 0. And it's convex too, right? If you have power of half, it will be non-convex, and you have another set of problems. So because of these nice things combined together, has been the favor of many researchers for the last 10 years, if not longer. So let me just make one slide comment on computation. And so in the first paper by Chen and Donahoe, I think they were using quadratic programming to solve for each problem. So if you look at the optimization, usually they don't try to select the tuning parameter lambda, it's solving for a fixed lambda. And then it doesn't make, you have savings you could make because the solution for lambda and the solution for lambda plus 0.111 or 0.1 might be very close. But if you call QP every time, you won't take advantage of that. And so later followed the so-called path-following algorithms. And there's Lars, I think very well known in the statistical community, and the homotopy method by Osborne, actually 2000. And like 2 years ago, somebody pointed me to a paper by Markovich of the fame of mathematical finance in 1957. So he has a path-following graph for a whole set of quadratic programming problems. So I'm sure there might be earlier references. And recently, for the large P, more than 100,000, is a lot of gradient-based method, which seems to be the winner in practice. And it's very active research. And there has been also quite a bit work on extensions, including us. We started this hierarchical penalty. So instead of just L1, you could have grouped L1, you could have L infinity. You could build in hierarchical structures on whether you want a different predictor to enter in certain order. So generally it's called structure sparsity, so that's very much active research. If you're interested, email me. I'll be happy to point you to the references. So here's kind of like historical overview. And the next few slides, I would try to give you some sense on one particular performance measure of this sparse model methods. So if you think about, if you want to understand Lasso from a theoretical angle, the first inclination would be like, let's assume there's actually a true sparse model, right? It's a separate question when your model is misspecified. And then you can say that I care about prediction error, and then getting particular things right or wrong probably doesn't matter. If two highly correlated predictors, I got the wrong one, from prediction point of view, it doesn't matter. So that's pretty lenient in terms of parameter estimation. You can have the parameters not right, but your prediction could still be good. And in high dimension, when P is large, most likely your predictors are very correlated. Unlike compressed sensing, you try to make things IID Gaussian, very orthogonal. In practice, you don't have the control a lot of the time. You don't have the design, therefore they're highly correlated. And a little closer to estimation is L2 error. So I want to estimate my loadings or coefficients in front of the predictors, right? And then this thing related to David Donald's talk is model selection consistency in statistics. It's trying to say, like, do you get all the non-zero betas correctly? Of course, most of the work, we did one work when the model is wrong, but most of the work assume you have the right structure, right? Assume model is sparse. It will be interesting actually to see when the model is not sparse, is that a good idea? Is that completely off? So I will just tell you a bit work, which, as I said, like we did a pretty abstract mathematical work, try to tie different earlier work, including ourselves, together. And actually, there's a very clear geometric picture emerging, so I just want to share that. So let me go like more general. Keep Lasso in mind. That'll be good enough. But I just want to show you that in general, in statistics, you don't have to take L2 loss, right? You can take any minus log likelihood. You can take any loss function. You can take Huber loss function in robust statistics. So that's my loss function. And regularizer, you don't have to take L1. You can take L2. That would be called ridge. You could take many other forms. So that's the regularizer. And my goal is to see under what model and what conditions my estimator will be close to the truth. Now, theta star, implicitly, I have a true model which depends on theta star. Okay? So this is the typical statistical estimation game. So it's the estimation, M-estimation with regularized, with regularizer R. Just think of L1. So the blue part, you think of L2, and the red part, think as L1. That'll be good enough. So here's a concrete example. I just not exhaustive list, so there's tons of work. If you're not there, I'm sorry, but I'd be happy to add if I So there's lots of work. So this is a model where we try to say that suppose the simplest model can think of, which is for prediction, which is meaningful is linear model. I'm assuming that I have a sparse model, means that I have, suppose for my neuroscience example, only a few filters, say a particular location, particular orientation, and particular frequency is really driving a particular voxel. Okay? And which is a reasonable assumption based on neuroscience, because we know that the neuron responses are very localized. So that's my big S, that's the red part, and the blue part are the noisy predictors. Other features, the filters from other locations, because I don't know a priori where my particular voxel is interested in. And then I put some noise because the model is inexact, and I assume it's kind of Gaussian. And that's the Lasso program. There's tons of work. Okay? But my P is much larger. It's almost 5 times as large as my N. And here's another example well studied in the literature. It's kind of motivated by the Netflix contest, but really, I think the winning team didn't use this method. Okay, so it's try to find a low-dimensional structure in the matrix by saying that, well, if a matrix, I have users, I have movies, cross, and I have a lot of randomly missing entries, which is usually not the case, right? People don't randomly choose movies. They like certain kind of movies. They are cluster structures. So you can, again, formulate that as a sparse kind of estimation problem and with a nuclear norm as penalty. This just show you how my general theory will cover. And this is related to Wavelet's talk. It's one version of doing covariance estimation, is to assume that the sparsity occurs in the inverse covariance matrix. In Gaussian models, if you have a lot of conditional independence, then the conditional independence will get reflected in the precision matrix, at the 0. So 1 and 4 are continually independent, giving the rest. You see 1 and 4, that's black, that means 0. So black means low, and white is high. So the stripe is kind of funny imaging defect. So it should be just 0 or non-0. Okay, so there's also tons of work. So that's another case. And so by about 2 years ago, we started wondering, I was involved too at the works with Lasso, with linear model and the covariance matrix. You see a lot of similarity in the derivations. There's some convexity needed, and there's some concentration inequality. But still, different problems seem to be a little different. So that's why there are many different papers doing different cases. So our attempt actually was very much want to teach in a graduate course and saying that, well, by the time you go to graduate school, you don't look at maximum likelihood asymptotic normality case by case anymore, right? By the time I went there, there's a general theorem with regularity condition and cover many cases. But if you go back 30 years before, it's people proving different cases for maximum likelihood. So that's what we try to do. So can we fish out a set of core ideas that will cover all these different cases? And it turns out to be the case, right? If the regularizer is as nice as L1, just keep that like some decomposable. You don't want to be tangled up, and then all the triangle inequalities wouldn't work. Okay, so we need that. And the other thing is you need strong convexity, but restricted. I'll explain why we need restricted. So those are the conditions actually need, and then everything just go. So why statistics and why we can estimate parameters, right? Suppose you have this curve you want to optimize, and that's the minus, you want to minimize. So it's the minus log of likelihood. So maximum likelihood, you take minus, you want to minimize. And as I argued earlier that the function in statistics we care about is a random perturbation of the oracle function, which we really care about, which is the infinite sample version of the loss function. Okay, so you know that your observed function is a wobble version of the true function. How much you wobble depends on how much noise or depends on how much information on the sample size. So when you have a key concept in statistics is Fisher information. And it's really just a curvature, right? It's a Hessian. It's a Hessian of this function you try to minimize. If the Hessian is really high, you have high curvature, then the wobbly on the y direction get mapped to a very small interval in your parameter estimation, right? The same amount of wobbly, because I said the function is wobbling because of random perturbation of the infinite version, sample version, then you wobble a lot on estimation. So you cannot estimate well the curve, the worse shape you are, right? That's why Fisher information captures how well you can estimate. Okay? And the sampling error gets killed because concentration or central limit theorem, depending on how you say it, but more or less the curvature still plays a role. So let's look at high dimension, least squares. So least squares, the Hessian is x prime x. When p is larger than n, x prime x is permanently degenerate. So you always have flat directions. Okay? So if you want to recover a dense parameter of p dimensions, you cannot do because there's always directions. You have no information, you won't be able to differentiate. So it's model identifiability problem. Okay? So basically that's why you couldn't estimate in general with n data points p parameters when p is larger than n because it's always degenerate. There's no curvature. There's always directions you cannot estimate. However, one key, I think, lesson from non-parametric statistics in the last 10 years is that if you look at the 80s, David alluded to that we have a lot of the minimax results, and people thought that in high-dimensional estimation is impossible because if your signal sits in the ambient dimension, it's true that when dimension gets large, there's not enough sample size. However, what we recently discovered is that even your unknown sits in high dimension, ambient dimension, but there's a low dimensional space either by a plane or manifold, then you pay a price to search for where they are, but you can still estimate. And that's basically what's going on. So when you do panelized least squares, And when the model is sparse, what happens is that you're forcing your solution to be in a cone, like the green part, when the two match. And suddenly, you only need convexity on that cone. Because on the ambient dimension, you cannot have convexity. There's always dimensions. And if the sparsity is relatively small to the ambient dimension, this cone is relatively small. So you only need now convexity on a small part of your space. And then if even your design matrix is Gaussian with some dependence, you can use random matrix here to show that you do have the convexity you need. And it's called restricted convexity. And that's why estimation still happens. And so you see the coupling of the true model sparsity and the correct penalty. These two doesn't have to be exactly the same, but there should be some matching. Otherwise, you won't be bringing down your estimator to the right space to cancel the noises. Okay. So if one lesson you want to take from here is that in high dimension, you don't need convexity in the whole space. You only need it on a smaller, if the model is low dimensional, and often you do have that. And that's why you can still estimate. And this is a formal statement, which I don't think you want to read. So here are just examples about decomposable regularizers. Again, just show you that for different problem, L1 is decomposable. You basically have two sets of split your subset of indices into two parts, and you can pull them apart. You basically want the sparse model part and the noise part to be separable, and then the triangle inequality will help you there. And we were hoping for something more general, but we felt like we're hitting the boundary. We don't have a proof that's necessary, but we have a sense that you cannot be completely general, this type of argument. And that's for low rank matrix. And so we recover the rate which appeared in earlier works, basically saying that you have this k log p divided by n as the rate. K is the sparsity, how many true, relevant predictors in your model. And P is the ambient dimension. For me, it's 10,000. And so we also have this factor of loss for different reasons, as in Xiaoli's talk, of log P. So the effective sample size become n divided by log P. It's good it's not n divided by P, then we'll be done. So it's log P, and the log P had a lot to do with the sub-Gaussianality of the tail of my Gaussian, the white noise in my model. So when the tail increases, you might lose the log P, but you might play with the loss function to recover some. So n divided by log P, in my example, so I have 1,700 data points. If I do the factor of log P, log 10,000, and that was 180. So I lost about tenfold observations. Okay, so that's useful. A little bit quick calculation formula for practitioners to see how much you really lose because it's penalty of search, right? You know it's 10 dimension, but there's so many possible 10 dimension space in a dimension of 10,000, then you lose. And the weak sparsity also mentioned in Donald's talk. You can do similar stuff, apply a theorem. So more or less you can recover a lot of the old results and get some new ones. And I think the generalized linear models is the most interesting, actually needs a more delicate argument than what I showed you. So that's we feel pretty happy that we simplified, and it becomes simple now. The old asymptotics I did maybe a couple of papers seems to be right in the middle of it. Now it seems pretty clear what's going on. Yes?
Does restricted strong complexity say anything about lower complexity methods like the decoding?
The what?
Does a restricted strong convexity say anything about lower complexity methods like not convex optimization, but like iterative soft thresholding or
No. No, but I think for those non-convex stuff like L-half or something like that, you can probably use Lasso to bring to the neighborhood, and then locally you convex again, so that will be applied locally, but not directly. So I think you can use Lasso to bring it to the right neighborhood, and then locally your non-convex optimization might be convex. Uh-huh. Not directly. You might be able to use it as some, as something in the college might be useful to you, but not a direct application. We really didn't address the algorithmic side. We basically says we proved theorem about the minimizer of this loss function with penalty. We didn't say how we get it. So the algorithm part is one student is looking at boosting. So that's more involved. And I think some of this will enter, but not in like apply the theorem type of thing. But I think the intermediate steps might be helpful. Okay, so back to the neuroscience example. So 1 week, I spent a whole year there, and I think a year later got a student interested. And so when Vincent Wu got on the project, Galant Lab was already publishing their Nature paper in using linear method. And so we kind of stuck, right? So first idea actually didn't work out, was that saying that we have this 10,000 images where we, can we take advantage of that? Can we use semi-supervised learning? Because maybe the image structure will help us to do prediction. But it turns out that with 10,000 images, with the high dimension we have, 10,000 just not enough at all. It's just too few to estimate covariance matrix. So it didn't really work well. It turns out RAGE works pretty well without estimating of the population covariance. And this, you see, ordinary squares doesn't work. That's just one based on generalized inverse. And boosting works pretty well, and RAGE works pretty well. And we really stuck. But the good thing about this exercise is that we can look at the selected filters and plot them on the image space and see where they are. So you look at the correlation preselection. You can see that you basically select a location on the image. So different voxels are interested in different locations. And you look at the boosting selection. It's more diffused. So you look at voxel 2. Seems like there are 2 spots that voxel was interested in. You look at the correlation selection, it's a marginal selection. It seems only interested in 1 spot. So both in terms of prediction, they give similar results. So it says that if it only depends on prediction, it doesn't really, you cannot trust just prediction models. Something else have to enter. And then there was this clear nonlinearity in our model. We did a residual plot. Sorry about the blurriness. I did a screenshot, which is not good resolution. And then Pradeep Ravi Kumar joined Berkeley, my group, and Martin's group. And he was doing thesis using sparse nonlinear models. He called SPAN models. Right? So it's an additive model. So you allow a nonlinear transform for each predictor, and you do self-thresholding basically to set some of the f's to be 0. Okay? So we did, detail I won't tell you because I think I want to go to the other project. You can see that we bring about 12% prediction across 1,300 voxels. So each dot is 1 voxel. We develop a different model. So definitely there's improvement. And then you look at the nonlinearities. You can see they all kind of have the same linear shape and then taper off. So it's kind of compressive effect, which makes a lot of sense for a real biological system, because even the intensity of the image keep increasing with no bound, your reaction to it, the brain reaction, cannot go off the chart because you only have finite energy. So it makes sense to taper it off. And later, when we revised the paper, Vince speed up the computation, but instead of using kernel density smoother, we use cubic spline, and we end up actually bringing more prediction gain. So we suddenly have 20% improvement. So you can completely just do better than the linear model. But you can say that, well, this is only prediction. Does that mean anything? So one thing people in neuroscience do is something they call tuning curve. So this also comes from physiology. They will shine a light at a particular spot and see whether the cell will respond. So we use our model, the linear model and the nonlinear model, and shine an artificial spot, basically have an input, and then see whether the reactions are the same. So you can see that there's some difference in the spatial domain. It seems like the nonlinear model for this voxel care about two locations more strongly than the linear model implied. And the spatial domain, you see the same thing. Again, it's a little different emphasis. So we just want to see that actually the two models are different. These are not conclusive. So we went to the decoding game. So we know we have 120 validation images, and we try to do decoding, use the forward model, and we start adding more and more noise images. Images where you know the subject was not looking at. And you see at the high noise level, you see a much better improvement of the nonlinear model. So this indicates that we capture something. Exactly what, I think we cannot really say. But this decoding says that in the beginning, actually, we do a little worse. But when you add more and more noise, the nonlinear model does beat consistently across different noise levels. Okay, but really, we really want to do V4, which is an intermediate area before IT, where you do object recognition, and after V1. That's where you have memory and attention matters, and that makes things a lot harder. So I really want to move to the next topic. So for this case, based on neuroscience, sparsity was a good approximation, right? We know Gabor Wavelet's 30 years of more research. But for the next topic from social science, I would say that it's more necessity. It's because we want to summarize things in a space that people can read, and we don't want to be very long. Whether you believe there's a model-driven, it's very, very hard to make that case. So we have to do some human validation for people to read our list and read the article and give us a score. So where we completely have to leave statistics. So this is a very schematic way you have to think the world works. You have things happening in the world, and people invest and report, and you have different things making decisions and then impact the world. Right? It's kind of nice. And there are different standards and practices about how we should do this. Right? You have the hero, Edward Murrow, who says that you should be believable, credible, and truthful. And you have the other end, Hurst, just basically willing to make up a lot of things. Right, so what we want to do here is to fill in some holes in media analysis. We were approached by a UC Davis professor who has been using the reading articles and basically summarizing the news. So it's very labor and time intensive. And, that's her view. I mean, whatever her experience, her training will really make a difference in what she will report. So we want to take advantage of machine learning because it's fast, scalable relatively, and hopefully everybody try to use it, have different results. So reproducible is very important. That's why we'll be recommending a sparse modeling method. But it's designed around predictive tasks. So we cannot really say, well, this method predicts well, then it's the right thing for summary. So that's why we end up doing a human experiment. So here the questions motivated us, right? Basically, she was asking the question, how Muslim has been portrayed in news media. Right? For example, it's like before, 20 years ago, you mentioned Muslim and terrorist. Probably people just say, why you put them together? But these days, I think people probably have heard them a lot together, and therefore there is a connection made. And you can ask the same question about a certain topic portrayed across different continents, across different media, like web versus printed newspaper. And you can also ask about different corpus of documents, say Republicans and Democrats in their party platforms. What are the things they seem to be concentrating on? So there's any group of documents you can ask the question, can we automatically summarize documents? Maybe as suggestive tools. And people, social scientists, can really do more. So our approach is actually turn this problem into a predictive problem by labeling certain articles, mention China even once, twice, and things. We actually try different ways and see which one was better into a predictive problem. And then we do the sparse modeling and choose a list of phrases. And then we actually run human experiment for people to compare what the article they read and then what's the list. Ask them, do you think this list represents what you read about Iraq? Okay, so that's what I'll end up doing. So this is a list when we took New York Times International Section 209 and then use our method, and that's the image we came out about China, right? So see, Beijing came out because probably a lot of things happened in Beijing. We couldn't figure out why contributed research was there, but it's there across different methods. You have global, Hu Jintao, the president's name, imports, Xinjiang, People's Liberation Army, Shanghai, Sichuan province, states run, Tibet, trade, Uyghurs, Wenjiabao, and Xinhua News, right? So from this, if you can guess that probably something to do with the protests in Xinjiang and Tibet, and probably People's Liberation Army was involved. That's one thing. Next step, right now it's all name entities. There's no action. The next would be 9 to 12 understanding, add some verbs, and see what they did there. Now I'm filling in what I understand what's going on. So how did we get this list? We showed it to our social science collaborator. She seemed to be happy. She's very eager. She feels like our tools. She wants to do this and that. We're not fast enough to give her the tools. So we have the New York Times article and about 9,000. So again, there are two choices. You can take the whole article as input, or you can take paragraphs. So which one do you do? And then we took one word and we ran overlapping interval to take 2-word phrases and 3-word phrases, and dropped all the ones only appear 5 or less in the entire corpus, the very rare ones. So we end up with about 200,000 key phrases. And we discovered in the database we have, there's duplications. So we try to remove that because there's the one when they made the database. And there's a lot of work, which is tedious but necessary for pre-processing, right? Do you do stemming? Stemming means China and Chinese. Should you merge them into one? We didn't. And the other is how should you count, like label. So after all the pre-processing, you end up with a huge but very sparse matrix. You have number of observations, which is count of, say, China, how many times. So one unit, one vector is one article or one paragraph. And then you have here is different documents. So cross is the different phrases, how many times appear in that article or paragraph. And then this way is the documents. And the big problem actually is about scaling, right? Because you don't want the length of the article to play a big role. So in the literature, there's something called TF-IDF from information retrieval. We tried that. Or we did our L1 normalization. And we also did the stop word removal. Stop words are the words that don't have a really meaning, like and, the, which will appear a lot, but it doesn't really tell anything because it appears everywhere. So that's one way to normalize. And labeling. Should you see one time China or Chinese appear, you call that China example, or should you do 2 times? Should you do 3 times? Should you only do 1, 3, and none, and put 2 and 3, throw them away? So we try different ways of labeling. So we try to try all reasonable ways of processing and to find a robust method which doesn't matter which one you do, because later you try to use this for different languages, then things might occur. You want things more automatic, resist all these kind of reasonable but arbitrary choices. Because the pre-processing is very different from the neuroscience example. There you have science. Here, all of these seem to be reasonable because we put artificial predictive framework on this. So we tried 4 different methods. One is co-occurrence. It's used a lot in information retrieval. So you look at China articles. You don't look at the non-China articles. You just see what appear most in the articles with something to do with China. And then you report those. Okay, that's called co-occurrence. So it has nothing to do with articles not in China. So for example, if there's something not to do with China but appear in both positive and negative examples, the co-occurrence will pick it up. Our method being discriminative won't pick it up because it's not discriminating. And correlation is just simple, very quick way of picking things up. So the first 2 methods are marginal. So there's no interaction. You just look at the key phrase one at a time and make a decision. Lasso, we heard, L1, LR is just like a lasso. Instead of least square loss, you do logistic regression loss. Okay, so it's more computation intensive. We end up doing lasso is because I was suggesting to the student that I know lasso works pretty well with 2 classes and it's faster. And it turns out also perform tiny bit better. So this is our flow chart. You decide whether it's the basic unit. Articles, we first actually start with the article, and then we did a conference paper. We said, why articles? Why not doing paragraphs? So we tried paragraphs. And then you make a data matrix, and you have to decide on the rescaling, stop words or TF, IDF. And then you decide topic, say China. And then there are different labeling options. Count 1 as positive, count 2 as positive, or hard count 1 or hard count 2. So there are 5 of them we tried. And then there are 4 methods to select phrases: co-occurrence, correlation, lasso, and L1, logistic regression. Then we have to decide how long we want the list. That's what we decide, like 15 or 20 words. Okay? So there are many, many choices in this problem, which you can look at prediction. And what we discover about predictions, if the method is really, really bad for prediction, then it's bad for human understanding too. But there's a range, about 70% prediction accuracy, then the prediction accuracy is not predictive anymore. Humans don't care about it anymore. Okay, so that's where we want to find other predictors to predict human performance. So that's what I said. There's so many choices. You have units versus articles versus paragraphs, the different methods, and you have 120 possibilities. Okay, so it's a huge amount of possibilities. And really it's hard to argue which one of the 120 will be the best. You can look at prediction performance, but that's different from human understanding. So clearly prediction is not the goal. And we want really data to really say we really want mimic humans. So we need human to enter. And we also right now try to find ways to predict what type of list human like, which we're not there yet. So human experiment is to have human read the documents, some randomly selected ones, and read our list. And then we also have prediction accuracy that human don't see. And then we ask a human, does our list correspond to your understanding? And you have a multiple choice. Okay, so it's a long questionnaire. And how we did it, we have to get the committee on human subject to prove our protocol to run anything on humans. That was a long process. And then we found that there's a lab in high school business, actually we can contract them to find subject and give them the questionnaire, and they will run the experiment for us. And that took a while. And then we have to design the web survey, right, to make sure that we're not biasing them. And they recruited 36 subjects. They are no way representative. They are Berkeley undergrad students who need money. And then we have to randomize, because you cannot possibly let each subject to look at 120 possibilities, and we have 15 country topics. You multiply that, It's just too long. So we did some randomization. I think everybody looked at 3 or 4 countries and some of the combinations. And then they actually did it in the lab, and now I'll show you some of the analysis. So this is a summary. So it's not, it just came out, so it's probably not a bad. So the higher the better. So I'll just leave it for 2 minutes and see what you see. So read that T means the TF IDF normalization. So this is compare different rescaling. Shall we stop means remove the stop word. R means L1 normalization. And this is the fall method. So this is averaged over all other factors. So you can see that T is on top. This is for article. This normalization method with article clearly doesn't matter which method you use. But Lasso, look at that. It seems doesn't matter which normalization you make. It's still a good performance corresponding with humans. So that's what we're pleased to see. And here again, you see 4 against Lasso. Consistently, doesn't matter how you label your articles. Count 1, count 2, what you call positive example, what you call negative. And 3 is not bad. It's another Lasso like L1 method, not as good. And here, T clearly is winning. But if you look at paragraphs, T is not surprising is winning because that's hand-tuned from information retrieval. People have thought and tried different things, and that's the one still standing. So it's not surprising. It works well for articles. But if you take shorter units, paragraphs, T suddenly doesn't work. Okay? And R now is better, L1. And here, with paragraphs, you don't have count of 3, basically. It doesn't appear in paragraph China 3 times, so there's why you have no data. And again, 3 or 4 are right there, and here R is better. But consistently, for article, we really like Lasso. It's robust against all this different reasonable processing we did. And that gives us more confidence to try a new task than T's, for articles, we'll be recommending T, but I don't know whether T will work for other languages, things like that. So that's the high-level summary, is that's something from the literature, which works well for articles. And for paragraphs, L1 rescaling beats this. And Lasso is robust. And L1, LR is not bad, but not as good as Lasso, and it's also slower. So it seems like there's no reason why you should do the more sophisticated, why have something simpler and faster. But this is heavier than the other 2 methods. So what we have to do now is that we want to look at for more text data, and really we need to have a web toolbox ready for social scientists to try and get feedback, see whether they like it. And one student want to really compare, say, coverage of China across newspapers from Europe, US, and China, and also across different time periods. And this method is pretty automatic, so you can do words from different languages. We don't really use the meaning of the words. And one thing I'm very interested in is actually we are working with the political scientists in Berkeley, and people have hand summarized the party platform documents for Republicans and Democrats. And that gives some validation. So we can do the automatic summarization and compare with what the experts have come out with. And the other thing a student is very interested in is that we know that prediction to a certain point doesn't really predict how humans like it. Can we find other features? Say, if the features selected are very correlated, that means they're kind of redundant. Maybe humans don't like it. Maybe humans like diversity. Can we come up looking at the list and have some idea whether human will like it, so that we won't have to run human experiment on any new task we take? And I'm very interested in this towards a bit sentences summaries than just name entities. We have a lot of places, names of organizations, but can we add some action, what the People's Liberation Army did there? So we need to add a little bit, the second maybe verbs and things like that. And so we have to build some hierarchical structure. One visiting student from France and a postdoc might have been working on that, but not ready to be shown. So here's a summary of the talk, is that The unified theory is really try to summarize a lot of the work, early work, and try to bring some clarity to what's going on, and hopefully something the malpractitioner also can understand and see what's the difference between estimation in low dimension and high dimension. And the science problem we've been working on for a long time, it has good subject knowledge relative to the social science problem, where we got the grant, the CDI grant, for 2-3 years now. We're finally writing the journal paper. It's really, really heavy duty in terms of the processing and what to think about, what reasonable thing to do, and convince ourselves that we're not just reading artifacts of particular method of processing. And I think it would be nice with all the work on sparse modeling to see more people try these methods and have some sense whether they work, how they work, and when they don't work. And the last and the most important are my co-authors. So the first work was work with Nevaga, a graduate student at Martin at Berkeley, and Ravi Kumar, John Postel, me and Martin, now at UT Austin. And the second part I talked was joint work with Gallant Lab, his postdoc, his former student, my student, my former student, my former postdoc. And this topic, imaging, is collaboration with Professor Al-Agawi and his student, my former postdoc. And a lot of money has been spent. So in terms of money per paper, it's really bad investment. Thank you.